Hey everybody, welcome back to Spatial. Anytime we can start with Mr. Rogers on a slide, I will do so. But we are starting a new unit today that very much has to do with first order neighbors, and it has to do with aerial data analysis. If you're keeping track, this is the third and final type of spatial data that we often deal with. We've now gone through geostatistical models, point pattern models, and now we're hitting up aerial data analysis and the models for aerial data analysis. So at first, we're going to talk about exploratory methods, and then next lecture, maybe 1.5 lectures from now, we'll get into modeling. Just a quick review about what we're dealing with here. Aerial data, we have our outcomes that are aggregated into some kind of discrete geographic areas. These could be counties. These could be states. These could be congressional districts. These could be census tracts. Honestly, the smaller, the better in terms of dividing that space into smaller and smaller regions. But oftentimes, if you're dealing with public data, counties and states are about as small as you're going to get. Congressional districts tend to be bigger than counties. You know, we're all thinking about the election, so why not mention congressional districts? So usually they're aggregated, not because it's good to analyze aggregated data. It's not, you know, we deal with things like ecological fallacy all the time, but it's to preserve confidentiality. For example, health outcomes, COVID. We'll be dealing with infectious diseases of different kinds. Just want to remind folks that there are other infectious diseases out there to worry about. COVID is a big one, of course. Voting records. You know, we want people to feel safe when they vote, so we will preserve their confidentiality. Financial data, average savings, average, their purchasing behavior. All of those things can be aggregated to preserve confidentiality of individual people. So remember our sort of adage of spatial correlation: similar data at similar locations. With aerial data, similar in locations will come down to adjacency. The other word for this is contiguity. So we will be paying attention about which counties, states, regions are touching, and we will define rules around those regions. So a lot of adjacency in our future, a lot of things like first order, second order neighbors, and of course, strong spatial correlation. You would be looking at similar data with neighboring counties, similar data with neighboring states, similar data with neighboring census tracts, congressional districts, etc. Here's the super simple heuristic. With point pattern data, we saw that clustering, so positive correlation, right, looks like points near each other. This was point pattern data. And in aerial data analysis, we're looking at nearby neighboring pixels, in this case, having similar values. Yeah, it looks like dark colors are around dark colors. There, there, and there, and there. Light colors around light colors, there and there. So that's a strong positive spatial dependence, strong evidence of clustering. We do have this concept of negative spatial correlation, and perfect negative spatial correlation, you think checkerboard pattern. Checkerboard pattern is not random. Checkerboard pattern, or chessboard, if you know you're on a white square, you know you are surrounded by black squares. If you know you are on a black square, you are surrounded by white squares. So if we look at the majority of the data, each square is surrounded by its opposite. That is not random. That is an example of a negative spatial correlation. To be honest, it's mostly, a mathematical possibility. There are a few. I can't think of a real life example off the top of my head that exhibits negative spatial correlation. Most of the time, it's either independent or it's clustered in some way. Now, if we think of And by the way, just reviewing point patterns, right? If I space my points out in sort of a regular grid of some sort, this is not a random point pattern, right? This is a regular point pattern exhibiting negative spatial correlation. Now, independence, you can think of as taking something that is clustered and taking something that is inversely correlated and averaging the two things together. And that's actually what we do here. This is a figure out of a paper or a textbook. So when we average the things together, we see that there are areas where it looks like there might be positive correlation, and some areas looks like there's maybe negative autocorrelation. So our eye can't really detect independence different from negative spatial correlation. Clustering is often easy to detect. Of course, we'll have statistical models to explain the sources of clustering, possible covariates that explain the clustering. But we often can't tell the difference between something that is not correlated and something that is inversely correlated, spatially speaking. Okay, so let's take a look at a really simple or a relatively simple example that is really close to home. So this is our good old state of Wyoming and 23 counties. All right, University of Wyoming is here in Laramie County. Yeah, there's the University of Wyoming right there. Cheyenne is right over here. That's a state capital. Yep, clearly don't belong in art school. So we have two major ways of defining neighborhood structure. One is through region adjacency, and another is through the using some number of nearest neighbors. So let me go through the first one, which is region adjacency. As I just said, we're looking for touching polygons, and we will be letting those polygons touch, be adjacent to each other, be contiguous with one another in two different ways. One is the queen method. I actually have, I forget the names of Wyoming counties, and I have them on another screen that I'm trying to keep awake while I'm talking about our good old state of Wyoming. I don't memorize the county names. There are 23. I don't know. I'm sorry. So there are two ways in which we'll be sort of dictating how our counties touch. One is the queen method, which calls our counties as being neighbors, being contiguous, being adjacent, if there is one point of contact. Formally, it's they share a vertex. The second one is the rook point of contact. If you have played chess, you know how the queen piece moves, and you know how the rook piece moves. So the rook piece requires two or more points of contact. So where that comes into play, really, is if you have a relatively, I'll say, relatively silly case of perfectly square counties, then the rook would allow for these two guys to be, yeah, that's right. These two guys to be neighbors, these two guys to be neighbors, these to be neighbors, and these to be neighbors, but would not allow for the cross neighborhoods, right? Because there's exactly one point of contact right here in the middle where my stylus refuses, absolutely refuses to behave. There we go. That is the exactly one point of contact that is accommodated by the queen and will not be accommodated by the rook. Now, practically speaking, in vast majority of analyses, we'll be using the queen contiguity because you're just trying to represent similarity of location. And there's no real reason, unless you have a really strong belief that, the corner counties shouldn't be counted as having similar location. Why not and let them inform each other's data? Practically speaking, can you spot the difference? So we have queen on the left and rook on the right. 23 counties. Can you spot the difference? It's right here, guys. Right? You're looking for crosses. It's these. In the rook contiguity pattern, this point of contact, this single shared vertex, is not counted. In the queen, it is counted. And so we're looking at claiming that Natrona County and Albany County, are neighbors, and Carbon County and Converse County are neighbors or not. And quite honestly, I don't know if it makes much of a difference. Most of the statisticians, in most papers that I've seen, use queen contiguity. Most of the code that I have on the bottom, you guys have already seen. Pull down county polygons of the state of Wyoming, project them using UTM-13. Centroids are little dots that are put in the middle of each county, and that just overlays. It's not required. It just makes it a point where the lines that represent the neighborhoods, the neighboring regions, can connect. We use a new package in this unit called SPDEP, which is widely used for areal data analysis. And here we use this poly 2 and B, which transforms a polygon to a list of neighbors. And here we have queen equals true, queen equals false. And then I can just plot them to make a pretty comparative map. Are there any borderline neighbors? Well, you think of having, while I'm still talking about Wyoming, there we go. So I can actually call out these counties. You think of, they're clearly smaller counties are well represented by their centroids. And that's a concept from point pattern analysis, right? When you're forming those dummy grid, you're trying to fit as many dummies as is reasonable into empty space so that every dummy can sort of cover its own tiny area. A centroid works very well for these counties in the northeast of the state, Crook, Weston, Niobrara counties. But when we start to look at the connection between this extreme northwest county up here, that looks like Park County, that's where Yellowstone National Park is, and its connection to Fremont County, you start to wonder how much similarity in location do those places share. There's a big old national park here, and Fremont County stretches, must be a diagonal, must be 300 miles, probably 250 miles. How much similarity in location can we really claim between these two? Look, we're trying to approximate, right? We don't have geostatistical data where we have a coordinate per observation. We have observations aggregated into touching discrete regions. And this is an imperfect way of sort of accounting for spatial correlation, nearby locations. So there will be some that are pretty uncontroversial, and there will be some that really should be questioned. So plot your data. If there is a lot that are questionable, or you have, say, you're trying to do an analysis in a place with 5 counties, then probably not worth doing. But 23 counties is probably pretty close to the cutoff. Any smaller than this, probably not worth employing too complex of a spatial technique. All right, moving on. A lot being said there. Our second major way to define a neighborhood structure is not to track which polygons are touching and in what way, or at how many points exactly they're touching. It's to find our centroids, right? Find our centroids, little points. I missed those two completely, didn't I? Find our points that represent the middle of every county, and then use sort of a nearest k neighbors. So nearest 1 centroid, nearest 2 centroids, nearest 3, all the way to however many you want. You are basically forcing, with nearest 2 centroids, for every county to have at least 2 neighbors. Every county will have at least 2 neighbors. So the nearest centroid is interesting because it sort of forms little cliques where based on the distance between the centroids, and that should, a question should pop up in your head, well, why should we care about distance between centroids? Well, we have to put the point somewhere to represent the whole county. So we're looking at Sweetwater County and Carbon County. In the nearest centroid neighbor, they're disconnected, and they don't become connected really, Sweetwater and Carbon, until we go to 5 nearest neighbors. At 3, they're still disconnected. If anyone's ever driven 80 west or east along southern Wyoming, at least qualitatively, those 2 counties feel pretty similar. So I would feel like they really should be connected. As far as, we're looking at Sublette County and Fremont County. I don't have a good sense. There's a big old set of mountains right here. I don't have a good sense for whether they should be connected, but looking at just the nearest centroid often creates these separate cliques. And so when you were doing the modeling and you're looking ahead, then these are going to share information. These are going to share information. These 2 are going to share information, but not with their east and west neighbors. Does that work? We're looking at Bighorn and Washakie. Yeah, there's a big old set of mountains right there. And there's the Yellowstone National Park right there. Maybe that makes sense. Maybe the nearest centroid makes sense for our good old state of Wyoming. But in general, I don't see much reason why we would want, say, these 2 counties, Sweetwater and Carbon, to be disconnected. But I think when we go to the extreme, make it 5, and by the way, we have this KNN to NB, so we just find K nearest neighbors using the centroids. Now you can change K from 1 to however many. I think the 5 forces every county to have its 5 closest neighbors. So the counties in the corners are going to reach out pretty far, won't they? So we have our northeastmost Crook County. It reaches out all the way over here. This is looks like Converse County, because we're asking it to have 5 closest neighbors. So oftentimes 1 is clicky, 5 is probably overconnected. What do? Well, a few things you can do. 1 is use your knowledge of the area, number 1. 2, don't worry about nearest centroids. Go with a queen or a rook contiguity, and then try and answer questions. Should we let these points count as similar locations? 3, you can fit a whole lot of these and use something like the AIC or predicting a holdout sample. There are ways of bringing statistical evidence into this equation. If you're asking me what I do, I use the queen contiguity, and that is reading the literature, what others statisticians seem to do. When I talk to geographers, they often tell me that it's too simple. It's too simple to claim if 2 counties are sharing a single point of contact or 2 points of contact that they're somehow related. So there are much more complicated ways of specifying neighborhoods. We are an introductory class. These are the 2 major ways, through queen or rook contiguity and really just queen, or through these nearest case centroids. But you have to make decisions that are defensible, and you can base those in something like an information criteria, in something like your knowledge of the area or prior literature. You could say, hey, about every other person who has done this analysis has used the queen contiguity, and so will I. That's science. Moving on. All right, so you have decided how you're going to count your neighbors. What do you do now? Well, you're going to encode this neighborhood structure into what is called an adjacency matrix. Most often it is a W. And that, I think the reason why it's a W is it's called this, sometimes called a spatial weights matrix. Spatial weights matrix. So you think of what is W. The adjacency matrix is kind of an areal data analysis version of our geostatistical, right? Think back to geostat, to point reference data. Right, so this is sort of encoding similarity in location. If we have geostatistical data, we use Euclidean distances, maybe semi-anisotropy thrown in. If we use aerial data analysis, we're going to use the adjacency matrix. There's a lot of similarities. It is also n by n, where n is the number of regions you have, with Wyoming would be 23 by 23. It too has zeros on the diagonal. So the distance matrix, taking a distance between a point and itself, that's 0, that's clear. With an aerial data analysis, you're basically saying that regions are not their own neighbors. I suppose it was written out right there. That's okay. And there are, I've seen 2 ways of specifying the adjacency matrix. By far, the most common is this binary one, where you basically, the ijth element of your adjacency matrix is 1 if regions I and j are first order neighbors. Just to beat the dead horse a little bit more, what you're calling first order neighbors can be either according to the queen-rook contiguity, or according to your nearest case centroid contiguity, or however, whatever other fancy way you choose to specify your neighborhoods. All of the counties that are first order neighbors are going to get 1, others are going to get 0. And so this matrix will have zeros a lot. A lot more counties are not neighbors rather than are neighbors. There is what is called a row standardized version of this, where what you give is not 1, you give 1 over the total number of neighbors. It is used for a few analyses, but I won't spend a ton of time on it because it's not particularly common. This matrix, the adjacency matrix, is very important because we will use it for spatial correlation, to quantify spatial correlation, and when we get to regression models later in this unit. So this is going to be a super important matrix. Pick your neighborhood structure, make your adjacency matrix, use it down the line. Let's visualize what this thing looks like. So here's an example with US states. That means our adjacency matrix is 50 by 50, right, n by n. The zeros on the diagonal. So notice, Alabama in the first row, they're arranged alphabetically here, has 4 neighboring states. So it has 4 1s, right? This is red or blue. The blue is 0, the red is a 1. Right? This is binary adjacency matrix. So that very first row has 4 dots. There are 2 dots here, 3rd dot, 4th dot. And if my geography, I can just look up map of the United States. All right, we're talking about Alabama. Very good. We're looking for 4 first order neighbors. So we start with Florida is touching, Mississippi, Tennessee, and Georgia. Those are our 4 first order neighbors. Alaska has 0 neighbors. So that right there is because it is not sharing a vertex with any US territory. Hawaii too has 0 neighbors. And actually, if you kind of focus in on that second row has no red squares. There are 50 rows and 50 columns, so it's a little difficult to see. So I highlighted that second row on the right. Maine has just 1 neighbor, New Hampshire. Let's flip back to our US states, and I will move myself. Maine out here in the Northeast is very close to touching, looks like Massachusetts, but it is not. It does not share a vertex with Massachusetts, so New Hampshire is its only neighbor. Now, here are the row standardized spatial weights. So the spatial weights are 1 over number of neighbors. So you can see there's exactly one of those that is a 1, right? Because Maine has just 1 neighbor, New Hampshire, and others are all between 0 and 1. Zero are, of course, zeros are, of course, for all the states that are not touching. Okay, so that's a visual representation of this adjacency matrix that we will see again and again as we get into modeling, especially. So geostatistics gives us the variogram. Point pattern models have things like the K function, Fry plot. Aerial data analysis has, among several such measures, the Moran's eye. So it was developed in 1950 by Patrick Moran, and we don't want to call him a bad name, so the emphasis is very much in the A. It's Moran, Patrick Moran. And it's very intuitive. It computes the average correlation of regions with their neighbors. And the way it's developed, in theory, the values are between -1 and 1. But I'll repeat, in practice, you almost always see positive numbers. We can compute in what is called a closed form. So we have a known computation that we can perform with pen, pencil, and paper. I won't require you guys to do it. Under the null hypothesis of independence. If we, as a null hypothesis, assume that our regions are actually independent, we can compute the mean and the variance of the Moran's eye statistic. And then we can turn it into a z-score. So under the null, we know how Moran's eye is distributed. That allows us to compute a classic hypothesis test, get p-values, get standard normal based confidence intervals. So it's popular because it can produce and give people a solid, quick measure of spatial correlation between your areal regions, your areal discrete spatial regions. It is known to have greater statistical power than other tests. I'll just name drop one. One is the Geddes-Ord G. If you may have heard of the Geddes-Ord G. Well, it is known to have lower power, and that's why we won't be discussing it. We're also in an introductory class. And if we go through every single spatial autocorrelation measure, then this will be a 5-year-long class. We'll be talking about the global Moran's eye first, which gives us an estimate for the entire study area, the entire state of Wyoming, the entire country of the US. But there are several extensions. One is what's called a correlogram. So it computes a separate Moran's eye for all first order neighbors, second order neighbors, third order neighbors. By the way, what are second order neighbors? It's the neighbors of our neighbors. If I go back to Wyoming and I erase my awesome mountains that I drew here. These two counties, Park and Teton, Jackson, Wyoming is right there. Park and Teton counties are first order neighbors. Then this county and this county are their second order neighbors. They're the neighbors of our neighbors. So we can compute a correlogram that computes a separate Moran's eye that, again, is just an average correlation between regions and their neighbors for a variety of orders. It's sort of trying to reproduce the same kind of thinking as in the geostatistical covariogram, trying to be like distance on the x-axis, correlation on the y-axis. That's where you're thinking. Then the other one is that I've seen used sometimes, is what's called the local Moran's eye. It computes a separate Moran's eye per region. Again, think back to geostatistical data, and it's okay that I say that because we're at the end of the course, right? We have to incorporate ideas from all three types of data. Our variograms are built, the covariograms are built by cross multiplying observations together. So this is somewhat of a similar concept where for each region, we're going to compute its correlation with its immediate neighborhood. And we do this for all regions to pick out sort of local clusters. Let me very briefly go through the formula. It is really prominently features a covariance in the numerator. Covariance is, of course, an unscaled correlation. Here we divide by the variance. Think about the variance as being divided by n, right? If we put 1 over n in the denominator, it flips. That's what the n is doing right there. The sums here are over just, this picks off only the neighbors. Picks off the exact neighborhood. These Wij's are what are sort of indicators that pick off our exact neighborhood. So we are performing, right? It's a covariance over the variance gives us a correlation, and it's an averaging that correlation over of each region with its neighbors. Under the null hypothesis of independence, it has a known mean. Interesting that it is a negative number. Of course, with, Wyoming has 23 counties. So under the null, assuming spatial independence, the mean is -1 over 22. So it's a very small number for any reasonably sized n, but it's interesting that under the null, the Moran's I has a negative value. So, of course, a negative Moran's I indicates negative spatial correlation. Positive Moran's I indicates positive spatial correlation. So how do we make a z-score? Well, here's our test statistic. Here is our mean under the null. All right, we perform hypothesis testing, assuming the null is true. Assuming null is true, the null being spatial independence, and we divide by the variance. We can take that z-score, compare it to the z-critical table, find a p-value, go back to intro to stats, and either reject or fail to reject the null hypothesis. Of course, it bears repeating that in many, many, many cases, the null hypothesis of spatial independence is a ridiculous statement. For a lot of, for COVID data, any kind of infectious disease, there's really little point of assuming as a null hypothesis that, the counties or whatever are spatially independent, right? So a hypothesis test and rejecting a hypothesis is only as useful as the hypothesis you reject. But that is performed. That is what the p-value that's associated with the Moran's I really tested. So what is my recommendation? Don't look at the p-value. Right, with a large enough region, even a small Moran's I test statistic will be significant. And I don't want you saying, oh, I have significant spatial correlation and my Moran's I is 0.17, woo, with a p-value of, 0.02. All right, I have statistically significant spatial correlation. I better go investigate. Moran's I is like a correlation coefficient. It's not exactly a correlation coefficient, but you can think of it as such. Correlation of 0.17 is almost negligible. So we really start paying attention when that Moran's I creeps up. Although it's never quite, I have not seen any case where it's like a 0.8, but don't go around calling it like a 0.1, even if it's significant, evidence of spatial correlation. All right, let's go through an example that is closer to where I'm from. Discussed Wyoming, where we all live and work. I grew up in the good old city of New York. I grew up right there, Ridgewood and Glendale. I went to high school in Lower Manhattan on the lower, by Battery Park, Chambers Street, by where the World Trade Center used to stand, Freedom Tower stands now. So, by now that I'm into health outcomes. So I thought I would look into two important infectious diseases that are not COVID related. There's enough COVID related analyses going on out there. So I'm looking at gonorrhea and HIV per 100,000 persons. And this data set has been uploaded along with the lecture to my courses. There are in New York City 195 what are called neighborhood tabulation areas. They are neither counties. New York is only consisted of 5 counties, Manhattan, Brooklyn, Queens, Bronx, and Staten Island. These are not census tracts. Census tracts are going to be smaller. This is a very New York-centric unit of analysis. So, but I wanted to show you that there are a lot of different scales at which you would want to perform an analysis, and there are a lot of ways of dividing space. You can use counties, and then you'd be stuck with just 5, or you can use neighborhood tabulation areas, in which there are around 195. So gonorrhea, HIV, you know, we can see there are a few hotspots. Apparently, I didn't realize this until I made this map. I was right in the, pretty close, apparently, to an area that has an elevated levels of HIV and sort of elevated levels of gonorrhea as well. Let me flip into R. This data set is pretty rich. I know some of you guys are going to be looking for data to analyze. And this particular data set that I've now downloaded and read in a shapefile that contains the polygon borders of my neighborhood tabulation areas. And I've joined it with publicly accessible data on that same scale. So there's a lot of variables that we could be looking at here. You know, some really cool and important demographics. And of those, I picked out the 2 that I have up on the screen, but there's so much interesting data to be analyzed. So this in no way you know, completes the analysis of this data set. If anything, just starts it out. Oh, and I wanted to demonstrate that there's, you know, a ton of possible covariates here. For example, rent. Rent could be a covariate, a proxy for maybe resources available to us, maybe sociodemographic status. So there's a lot in this particular data file. So we're going to go through, and first of all, once we pick an outcome variable, so in this case it's gonorrhea and HIV, gonorrhea on line 77, HIV on line 79, I want to only retain those polygons that don't have an NA. By the way, there are some missing polygons here. And if we zoom in, if any of you are familiar with the geography of New York City, we have JFK Airport here. We have LaGuardia Airport here, Rikers Island, it's a jail. We have Central Park. We have a large swath of cemeteries, including the final resting place of Harry Houdini is there. Some looks like that is an unpopulated area and some wetlands there. So if they're not missing because I have bad data, they're missing because they're parks. And so parks, of course, don't have rent. Parks don't have gonorrhea or HIV. But to analyze our data, I need to only retain those polygons that are not NA. And I do that right there. So first things first. I have to decide on my neighborhood structure. You will notice that by excluding NAs, I have these kind of holes. I've made NAs and parks. I've made these kind of holes. And so the neighborhood tabulation areas have to connect around the parks. Here I have on the left the queen contiguity. So I'm counting a single point of contact as the 2 regions are first order neighbors. Here I have Rook continuity, which requires 2 points of contact. It's hard to spot because we have 195, 181 regions left after I excluded, you know, airports and jails and whatnot. But we actually add 22 links if we use the queen contiguity. And it took me a very long time to spot where that occurs. The difference between the two lies in Lower Manhattan. And if you look particularly closely, there are these X's, right? When we have some irregularly shaped county, maybe another, maybe another, maybe another, the difference lies in whether these cross neighbors are counted as neighbors. And so the difference lies in Lower Manhattan when we have these relatively small neighborhood tabulation areas. So if I zoom in, maybe there are others that I didn't spot, but basically these kinds of cross patterns that occur throughout the more grid-like Manhattan borough. You know, which one do I go with? Quite frankly, I have no problem letting, you know, northeast and southwest neighbors be neighbors, especially in the same borough. You know, you will notice that, interestingly, I form connections across the East River. East River comes down right over here. So recognize this is a more complex geographic circumstance than the state of Wyoming. The state of Wyoming, yeah, there are beautiful mountains, but the state is, I think it's easier for me to sort of just go with a particular neighborhood structure because, you know, it's fairly rural. And here, though, do we let our neighborhood structure cross a river? Do we let it cross? What about here, where there is Roosevelt Island in between? You know, do we only let it cross where there are subways connecting the two boroughs? So there are some decisions to be made. I don't edit the adjacency matrix manually, but if I was working for the city of New York, I might have to. I imagine they have an official one that they use in their epidemiology or demography department. You know, and then we have this case where the regions are forced to connect around the parks, not through the parks, right? Clearly, if I have Central Park in front of me, I can walk through Central Park. But because we're counting touching regions, two regions that are apart from one another are not connected. So we have to understand these as possible limitations for what we're trying to do. And then remember, I had to exclude all the NAs where a neighborhood tabulation areas reported an NA for its gonorrhea total, not a 0, an NA. So the question to ask is, are the NAs really zeros? You know, for example, out in Staten Island here, is my NA a park? It's not a park. At least I don't think it's a park. I think I'm missing one of these two. It's definitely not a park, so I'm getting an NA for gonorrhea for that area. I had to exclude it from further analysis. All of these are the kinds of questions we want to ask when we're defining a neighborhood. Definitely plot your neighborhood. Make sure you are at least okay with what is being imposed. The other one is here in the Rockaways. This area is called the Rockaways. And you can see, well, geographically, it's sort of disconnected a little bit from New York City proper, but it is perfectly fine connected to Long Island. This is Suffolk County here on my right. But because of this sort of marshland, it's sort of disconnected from New York City proper, and we have JFK here. If I use my Queen or Rook contiguity, these three neighborhoods are sort of out on their own. Knowing a little bit about the area, I'm actually okay with that. Here we have Staten Island. It's out on its own. Well, it's actually an island. So again, I'm kind of okay with that. Manhattan is connected to other two boroughs. So being from New York, I am generally okay with this neighborhood map. So when you're analyzing your neighborhood map, I want you to apply common sense, plot your data, and make sure you're okay with the neighborhood structure that you're imposing. I can also take a look at what happens when we're looking at the nearest centroids. Yeah, I didn't think too much about, how different this is. I mentioned several times the queen contiguity is sort of used a lot. I thought it was interesting that the island of Manhattan seems to be disconnected with k equals 1, but with k equals 2, we now get the connections with Far Rockaway, and this is Brighton Beach area of Brooklyn. I went with the queen contiguity. You guys can fight me on it if you want, or grab my code and perform exploratory analysis. I actually look at 4 different neighborhood structures to see how the neighborhood structure I use, whether or not it changes my my outcome. So let me flip back into R. I'm trying to compute the Moran's I coefficient. I'm trying to determine if my gonorrhea incidence, trying to determine if my gonorrhea incidence, so the map on the left, is significantly spatially clustered. We think it is significantly spatially clustered. I can visually identify at least 3 or 4 or 5 clusters. We're looking for high incidence among other regions of high incidence. We're looking for low incidence among regions of low incidence. So I think I'm expecting pretty strong spatial correlation. So the code, we use the Moran test function. I give it my outcome variable. And notice this, of course, excludes NAs. And then I use this NB2 list, which is the neighborhood structure to a list of neighbors. It's just sort of a workflow that we have to develop with this SPDEP package. There's not a good way to sort of intuit it. That's why I provide my code to you guys. So I go with nearest 1 centroid to 5 centroids, and I have the queen contiguity. So here are my centroid-based Moran's I. I get 0.589, 0.48, 0.45. So all 3 indicate that we have, well, these are correlations, right? So our neighborhood tabulation structures share about 59% of the information with their nearest neighbor. They share 55% of the information with their 2 nearest neighbors, and 54.5% of the information with their 5 nearest neighbors. So that Moran's I is diminishing because we are introducing more and more different neighborhoods that are no longer quite in the same exact region. The 2 nearest neighborhoods, very close to one another. 5 nearest neighborhoods, no longer. But look, the Moran's I, it decreases, but only very slightly so. On the other hand, the variance decreases. As variances tend to do when our sample size increases. As we introduce more neighbors, our variance diminishes. But our conclusion stays the same. There's strong spatial correlation. And I'm saying strong because of the magnitude of Moran's I. It's bounded between -1 and 1. 0.589, 0.48, 0.45 are pretty strong. And those p-values are all teeny tiny. So I'm not even looking at the p-value. I'm looking at the Moran's I relative to its variance. And it's quite large relative to its variance. Strong spatial correlation. We expected it by looking at a map. What do we notice about the statistics and their variances? As we introduce more disparate areas, Moran's I tends to decrease, as does the variance. What happens with the queen contiguity? Well, you know what? It didn't change the game. It didn't change our conclusion. Moran's I is somewhere in between. It's somewhere in between. Well, in fact, it's No, I'm wrong. It's the largest of the three. And the variance is somewhere in between 5 and 2 nearest neighbors. So in this case, it doesn't matter which neighborhood structure we go with. Let's take a look at another way of specifying what the Moran's I represents. Remember the adjacency matrix, W, right? It's n by n, zeros on the main diagonal, and the ijth element is 1 if the two regions are touching, 0 otherwise. We can create what is called a spatially lagged version of any variable. So by pre-multiplying our variable by our adjacency matrix. So this is kind of the outcome of our neighbors. It's spatially lagged by 1 nearest centroid. Then if I plot my original outcome variable versus its spatially lagged version, we expect them to share a lot of information because we're just looking at the one neighborhood region. I just used ggplot2 to fit a regression line through these data. Again, this is the outcome variable versus its spatially lagged version. The slope of that line is our Moran's I. Here is my code. The slope that is reported is 0.5892. That's using the nearest centroid adjacency matrix. 0.5892 is the slope of that line. 0.5892 is the Moran's I statistic that is reported right there. So that is another way of thinking about the Moran's I. Corellogram, to finish up this particular lecture. We take our approach, Moran's I, average correlation between a region and its neighbors, and we extend it to first order neighbors, so second order neighbors, third order neighbors, etc. I think that this is meaningful, and up to how many orders you specify right there in the code. I think this is meaningful in areas where it, having, for example, fourth order neighbors where Moran's I goes to 0. Think of that as the range, right? In geostatistical data, when we were looking at the covariogram, where it hit 0 was our range. So for the gonorrhea, it looks like fourth order neighbors become spatially uncorrelated. But everything before that, well, was at least somewhat spatially correlated. In fact, second order neighbors were still correlated at a clip of 0.25. First order neighbors, almost 0.5. So I think this is particularly useful when we could, it's meaningful to look at something like a fifth order neighbor. With 190 regions of New York City, the neighborhoods of New York City, it is meaningful to look at fifth order neighbors. With 23 counties in Wyoming, it is not meaningful to look at second, it probably is meaningful to look at second order neighbors, but once we get to third order neighbors, we've probably covered the entire state. So this is really useful for larger regions where we can pick out, looks like it takes up to 4 orders of neighbor structure for us to stop sharing information about gonorrhea incidents. I've repeated this with HIV, and for comparison purposes, I really wanted to have one that is independent or really noisy. And I came pretty close. It's the no insurance under 18 variable. But gonorrhea and corellogram, they look very similar, don't they? And if we actually go back up to our map of the two variables, well, they are generally elevated in the same areas, and they're generally lower in the same areas. Maybe this northern tip of Staten Island is the only difference in terms of HIV. That's not elevated that much on the gonorrhea side. But there also is a common thread between the two. They're both sexually transmitted diseases. If people partake in risky behavior, if they don't use protection properly, there might be liable to get both conditions. And so we should expect there to be a similar underlying risk factor for both HIV and gonorrhea. And that is really nicely reflected in the similarity between their correlograms. It takes around the fourth or fifth order neighbor for both of them to, for the Moran's eye to go to almost zero, but they both tend to be fairly strongly, moderately correlated at first and second order neighbors. When we look at the no insurance under 18, it's not good, right? Yeah. I'm not going to argue with you if it's better or worse than gonorrhea, but it's not good to have a child with no insurance. You can't treat them for a large swath of maladies. But you look at the fact that this particular correlogram looks nothing like the other two. Yes, there is statistically significant, technically, spatial correlation at the first, well, call it 4 neighbors, but the magnitude of that correlation is quite a bit lower than that of gonorrhea and HIV. So should we be surprised? I don't think so. Let's verify. Here are some maps. Remember what positive correlation looks like? Clustering, right? Positive correlation, clustering, high amongst high, low amongst low. High amongst high, low amongst low. Look at the no insurance under 18. It resembles very much something that looks like a checkerboard pattern. There are some areas where there are a lot of children that are uninsured, but they're around areas where children have some insurance. And so there's a lot less clustering here. Less apparent. Clustering. And so the lack of clustering is reflected by this correlogram, looking quite different than for our 2 sexually transmitted diseases. All right, enough of disease for today. Next time, I will finish these slides talking about some of Luke Anselin's work, and we will get into preliminary modeling exercises. So you guys stay safe. I hope that none of the maladies we discussed today strike you, and yeah, hope to see you guys next time. Move myself, stop recording. All right, thank you guys. See you next time.